Just take a look at the metal all around you. Could be a fork, a car door, even something as simple as a paperclip. They all seem, well, solid, right? Simple. But what if I told you that inside every single one is a hidden world? A whole microscopic landscape that basically decides everything about it. Well, today, we're going to dive in and uncover exactly that.
So here's a great question to kick things off. What makes a paperclip bend, but a knife blade stay sharp? I mean, think about it. A paperclip is made of steel, and so is a really good knife. So why can you twist that paperclip into any shape you want while the knife is incredibly hard, strong, and holds that razor-sharp edge? The answer, as it turns out, isn't something you can see on the surface.
Because the secrets are all hidden inside. Just look at this. On the left, that's the internal structure of the soft steel, from our paperclip. And on the right, that's the hard steel from the knife. I mean, they couldn't look more different, right? These incredibly intricate patterns are what we call microstructures, and that is the key. This right here is the metal's hidden identity.
Okay, so to actually see this hidden world, we need a very special tool. This is a metallurgical microscope. Now, it's not like the biology microscope you're probably picturing, where light shines through a sample. Metals are opaque, you can't shine light through them. So this one is designed to shine light down onto the surface and then capture the reflection. It's literally our window into the metal's secret world.
All right, so we have the right tool for the job, but you can't just grab any old piece of metal and stick it under there. Oh no, to really uncover its hidden identity, we have to prepare our subject first.
Yeah, you really can't just put it under the microscope. A raw piece of metal fresh off the cutting block, it's a total mess of scratches and all sorts of imperfections. Its secrets are completely locked away. So to unlock them, we've got to follow a really careful, multi-step process.
Think of it like a little journey we're about to go on. It's a 5-step process that's going to transform a rough, kind of ordinary piece of metal into this scientifically perfect surface that's ready to spill all its secrets under the lens.
So here's the roadmap. First, we cut out a small piece. That's called sectioning. Then we stick it in a little plastic puck so it's easy to handle. That's mounting. After that, we smooth out the surface, first with grinding and then with polishing. And then finally, we get to the most important, the most crucial step of all, etching.
This hand-drawn diagram gives us such a great overview of the whole journey. You can see the cutting wheel, the press for mounting it, the grinding and polishing stages. It's all leading up to that final peek under the microscope. And trust me, every single one of these steps is absolutely essential to get to the truth.
Let's zoom in on grinding and polishing for a second. Now, they might sound kind of similar, but they are worlds apart. Grinding is basically the brute force part of the job. You're using coarse, abrasive paper to get rid of all the deep damage from the cutting stage. But polishing? Polishing is the fine art. Here, you're using a soft cloth with these tiny, microscopic diamond particles to erase every last little scratch until that surface becomes a flawless mirror.
And this is what you get. After all that hard work, we have a perfect mirror. It's incredibly smooth, totally free of scratches. But here's the crazy part. If you put this under the microscope, you see nothing. Absolutely nothing. The secrets are still hidden. We need one final step. It's time for the big reveal.
Okay, this is easily the most exciting part. This is where the real magic happens. We are about to transform this completely featureless mirror into a detailed, complex map of the metal's inner world. And there it is. This is that aha moment. On the left, you see our perfect polished mirror, totally blank. And on the right, that is the exact same surface after just a few seconds of etching. Suddenly, a whole universe of shapes and boundaries just appears out of thin air. This is the microstructure. So what exactly is this magic step called etching? Well, it's basically just controlled chemistry. We apply a really mild acid, we call it an etchant, to the surface. Now, this acid doesn't just eat away at the surface evenly. No, it's much smarter than that. It actually attacks different parts of the metal, different crystals, or grains as we call them, at slightly different speeds.
So how does that make it visible? Well, the etching process carves these microscopic hills and valleys all across the surface. So when the light from the microscope hits this new bumpy texture, it scatters. Grains that are angled one way might send the light away from the lens so they look dark. Other grains might reflect the light straight back up so they look bright. And just like that, you get the contrast you need to see the entire structure.
Okay, so we've successfully revealed the map. Now it's time to learn how to actually read it. What are all these light and dark areas? What do all these different patterns mean?
Let's start decoding the microstructure of steel.
So the first big feature we're going to look at is called ferrite. You can think of ferrite as the base ingredient in steel. It's basically pure iron, and it's the stuff that makes steel soft and ductile, bendy. Under the microscope, it shows up as these light-colored, kind of polygon-shaped areas. We call those grains.
And here is a perfect example. This is a micrograph of low-carbon steel. Yep, the exact kind of stuff that's in our paperclip. You can see it clear as day, right? It's almost all those large, bright grains of soft ferrite. And that is exactly why it's so easy to bend. Okay, but what about all that dark stuff? Well, that is called perlite. And let me tell you, it is a total game changer. It's not just one thing, it's actually a composite. Imagine a superfine, layered sandwich made of soft ferrite and this incredibly hard, almost ceramic-like stuff called cementite. That combination makes perlite way, way stronger and harder than ferrite is by itself.
Now, take a look at this. This is high-carbon steel. We're back to our knife blade. See the difference? It's just incredible. It's almost entirely made up of that dark, complex perlite. You can kind of see the ghosts of the old ferrite grain boundaries, but the whole structure itself is just packed with strength.
All right, so we've met our main ingredients. We've got the soft ferrite and the hard perlite. Now let's bring it all together and see how the specific recipe for steel creates the final product we see and use every day. So here's the crucial takeaway. It all comes down to one thing: carbon. Carbon is the key ingredient that creates that strong perlite. So low-carbon steel has very little perlite. It's mostly soft ferrite, which is why it's so ductile. High-carbon steel, on the other hand, has a ton of perlite, which makes it hard and strong. And medium-carbon steel? Well, just as you'd expect, it's a balanced mix of both. The recipe determines the structure, and the structure determines the properties. It's that simple.
And hey, this isn't just a cool theory. Scientists and engineers actually use machines like this, a hardness tester, to physically prove this connection. What they do is they press a tiny, super hard point into the metal's surface, and then they measure the size of the dent it leaves behind. A smaller dent means the material is harder. It's a direct link between what we see in the microscope and how that material performs in the real world.
And that, right there, is really the big idea behind all of this. What's happening at this tiny, microscopic level has a gigantic impact on our macroscopic world. The tiny, completely invisible structure of a metal is what determines its giant real-world strength.
So, the next time you pick up a paperclip or a wrench or even just your house key, take a second and remember that complex, hidden landscape that's buzzing with activity right inside. And it really leaves you with a pretty cool question, doesn't it? What other hidden worlds are just waiting to be discovered right inside the everyday objects all around us?